Okay, so we're now on to our first problem. So we're asked to compute the derivative for this specific function, x squared plus 5. Looks a little funky on my screen. But again, remember, we're told we're using the definition. So that means we want f prime of x equals the limit as h goes to 0 of the difference quotient. Because we're solving this algebraically, we're not letting h equal 1 and then 0.1 and 0.01, 0.001, etc. We're going to leave everything here symbolically and solve it for this particular problem. So we're going to focus first on just the right piece, which is the difference quotient, and that means that first we're going to simplify the difference quotient. I like to think of the difference quotient as 3 parts. We've got this f of x plus h in the top part. So knowing that we're simplifying x squared plus 5, I'm going to write the function x squared plus 5, but my input, instead of just being x, is x plus h. So I've now put x plus h in where x went. And I'm ready to move on to the top right part of the simplified difference quotient, which is to subtract the equation. And again, our equation is x squared plus 5. So I'm subtracting x squared plus 5, but where x is, this time they want x. And then, of course, the whole thing is all over at h, so I said divided by h, and I now have my initial filled-in difference quotient. But we need to solve this algebraically. So as I continue this down to the next line, I need to start with this x plus h quantity squared piece. And over here we have this reminder in the top right that says whenever you have a binomial squared, instead of writing the binomial twice and doing FOIL or distribution, we have the formula that it's the first squared plus the last squared plus 2 times the first and the last. So focusing on just x squared plus h, quantity squared, I'm going to have x squared plus 2xh plus h squared. And then don't forget, I still have the rest of that bracketed piece, so I need to put my plus 5. Now I'm ready to move on to the second half of the numerator, but I'm going to need to distribute that negative sign to the minus f term. So I now have minus x squared minus 5, and the whole thing is still over h. So I had my initial filling in of the difference quotient. I now have an expanded form of the difference quotient, but now I need to work on cleaning this up, and so we begin with just the numerator. Don't cancel too many things at once, because mathematically that's not technically correct. So everything that's on the right side, the f of x piece, is always going to cancel. So my blue x squared minus 5 better cancel. Well, let's look. Yeah, I have a positive x squared and a negative x squared, so that adds to 0. I have a positive 5 and a negative 5. That's going to add to 0. As you have been or will be told, please don't just cancel terms off, because it's one of those things that when you go to cancel the 5s and do it like this, it really just looks more like plus 5, and it's hard to read your work. So I use some different notation to indicate where I'm canceling. So now that I'm going to add those like terms, which I'll add to 0, I have just 2x squared plus h squared all over h. And every term, wrong color pen, sorry. Every term has an h in it, which should always happen after you've completed all your canceling. So that means we can actually cancel h's next. One of the best ways to do that is to factor the h out of the top, because this would give me 2xh, which is what was originally there, and h times h is h squared. So now I can go ahead and cancel h's, and I'm left with 2x plus h, and this is the simplified difference quotient. So quite a few steps. I'm not done because I still need to take the limit of this, but I finished one of my major goals. So now we can take the derivative. We've got our simplified difference quotient, and we're ready to find f prime of x equals the limit of that simplified difference quotient 2x plus h. So the limit as h goes to 0 part is going to go away at the exact same time the h goes away. Basically, think of h as turning into 0, but it can only turn into 0 when the limit goes away. So the limit will go away and the h term is going to go away. So now we just have the f prime of x equals 2x. This is our answer. Okay, so now let's make sure you understand what just happened and what the derivative really means. The derivative is also a function, right? It was 2x. And that is because it is the slope of the tangent line. And since there are many tangent lines, there are many slopes. So let's look at it. We are working with the equation x squared plus 5. So if I was to graph this, I have an upward parabola at transposed up 5. So here is my x squared plus 5 equation. My derivative is the slope of a tangent line. So let's take this tangent line just randomly over here, where I'm focused on the 2x derivative, giving me the slope of this blue tangent line touching the outside of my graph. So let's say that point was at -4. I'd plug in a -4, and it's kind of like saying the slope of that line is -8. Keep in mind, negative slopes go down and over, so it follows that pattern. But remember, there's a gazillion tangent lines we could draw. Over here at x equals 1, my tangent line using 2x, where in this particular problem we decided to let x be 1, is 2. So using the derivative f of x equals 2x, I can find all sorts of tangent lines in a gazillion different spots on my graph.